with the last part of the course, which basically is what to do if you have to analyze more than one time series. So basically, we will start talking about Vivariate Analysis, which is the information, for instance, that the bank will ask to give you a loan if it wants to know your financial situation and your partner. And then we will finish with multivariate, which will be not only your partner, but some other people in your family. So a group of things that are looked at it all together. So Vivariate, the most well-known measure for Vivariate analysis, and you should always start here, is to calculate the cross correlation. In this expression, it's very simple. That's because before doing this calculation, you need to remove the mean value and normalize to the variance equal to 1. So in that case, the cross correlation is just the product. The average of the product is a number between -1 and 1, is symmetric, and you can calculate it with a lag. This lag gives you information about how you have to move the two-time series so they are best aligned. And the Pearson coefficient is defined as the absolute value computed at lag 0. Let me give you an example. Go back to this. Yes? How to, I think you are asking about how to select the tau.
Yes, yes.
Maybe how to choose this value here. Yes? I'll give you an answer in a minute. Okay. So let's consider 0 tau. Forget about tau for the moment. And do you remember this stochastic resonance that we talk about when you have a small amplitude signal and the response of the system follows the signal for optimal level of noise. So this is the signal, and you can see that here there is maximum correlation. So basically, that's how you quantify this effect. The stochastic resonance, one of the ways to quantify is to calculate the cross correlation as a function of the noise. And here we have very low correlation. And for a lot of noise, there's also very low correlation. And for an optimal level of noise, you can see that it's a correlation almost equal to 0.8. And again, the lag. Going to the lag, suppose that you have two time series. Here is in somewhere in Argentina and in the sea. You clearly need to understand that there is some lag between what happens in one point and what happens in the other point. This is I think it's temperature anomalies. And you just see this, and it's obviously not obvious which is the lag to consider between the two time series. But if you do this as a function of the lag, and in this case you change the lag between -200 days and 200 days, you can see that there is a very important peak a few days. So this gives you some information about the fact that there is a lagged correlation between what happens in these two geographical regions. How to select the lag? You just have to try. Basically, if you don't see an important peak, then you might need to increase the range, or it might be that there is no correlation. Okay? I don't know if that answers your question.
Yes, more or less.
It's a function of tau.
Sample evolves from finite from
of course.
You must use some sample theory, like Shannon theory.
Yeah.
Sample theory.
Yeah.
And then you let your intervals of discretization is constrained by this kind of theory. And then I ask you how to choose your time length from mathematical point of view.
Okay. I need to think about it. Maybe we can talk about after the class. But maybe I think we can see this when we talk about the mutual information, perhaps. Perhaps. Okay. So again, it's a function of a lag, and you just choose search for this maximum in a given time interval. And this time interval is a parameter. When you're looking for maximum correlation, you need to always specify which interval did you look for, because the peak can be somewhere else. If there is a system with a long delay, there might be some recovery later on. So it's important to know about your system when you choose the interval of tau values. Okay, so again, as it happens with the autocorrelation, you need to remember that this gives you only linear relationships. And there might be nonlinear relationships which you're not seeing. So cross-correlation equal to 0 doesn't mean a lot. You always need to go and look at the data and plot one point versus another point. The other thing is, yes, correlation is not causality. And I think almost everybody knows this, but I really like this example and I want to put it again. So you have the number of sunspots in the sun and the number of Republicans in the US Senate. Okay? Clearly no relation, but if you don't have a large number of data points and you plot them together, these plots might look like they are correlated. Okay? If you compute the correlation, it will give you a 0.52. And a lot of people say, oh, the significant threshold is in 0.5 because the correlation goes between 0 and 1. So 0.52 might be significant. Of course, it's not. It's not significant. Once you do the appropriate surrogates, you test the value that you expect just using surrogate data, you will see that this is perfectly within the range of values you expect for correlation when you don't have actually any correlation. So you cannot infer any causation from correlation. And if you want to have fun, well, if you want to really read seriously about this, I strongly recommend you this paper. It really tells all the story of the sunspots and the US Senate, Republicans in the Senate, and explains with all detail the type of surrogates you need to use. And there's also a really funny list of spurious correlations here. If you take a look, you laugh a little bit. Okay, so the mutual information is a nonlinear correlation. Okay, it gives you, it captures correlations which are not seen by the cross correlation. This is a mathematical expression. Again, you can derive this from some principle like the joint entropy. But again, I'll give you the reference later. It's not difficult to see that if the two variables are independent, fully independent, then the joint probability is the product of the probabilities, and then the mutual information should be 0, because you have logarithmic of 1. Otherwise, this is, by definition, a positive magnitude. And that is a problem, because it is unlikely that in real situation where your data is limited, this is going to be the case. We will see in a minute. You can also compute the mutual information with a lag, meaning you can compute the probability of X taking some value at time t, and Y another value at a different time. And it can also be computed from symbolic probabilities. So you can do symbolic analysis first, and then calculate the probability that a pattern 1, 2, 3 appears in one time series, and in the other one you have also the same pattern or not. Okay, so this is an example of why you need to look carefully at the mutual information. What does it mean, a positive value? Because if you have two time series which are completely random, and this in this case is 300 data points that are generated with random between 0 and 1, there's no correlation in any variables. Once you can compute the mutual information using this expression, so you have to use bins, you have to calculate the joint probability of this bin, and then the probability of X, the probability of Y, which is basically the number of particles in this box, and then the probability of X, which is this column, and then the probability of Y, which is the row. Basically, you get, and you repeat this many times, you don't get always the same number, obviously, and it's distributed, and you have a positive value of 0.15. So this at least gives you an idea. A simple way to perform a significance test, if you don't want to generate surrogates, or surrogates complicated, is saying if you have two time series and you get a mutual information of 0.25, you can be sure that there is some, really, they're not independent. But if your value is, I don't know, 0.12, it's within this range of values. So you can say, well, I don't know, that might be completely independent and you still get 0.12. So any value higher than this 0.2 can be considered significant. But of course, the 0.2 is under these conditions. You have 300 data points. This depends on how much data you have. So you really need to do appropriate significance test and have a lot of data if you want to reduce this uncertainty. There is a relationship between cross-correlation and mutual information. So in some cases, they are redundant. If the data is Gaussian, if the two processes are Gaussians, they are directly related by an equation, which is this one. So you don't need to compute both. If you're dealing with Gaussian data, the mutual information doesn't add anything. In general, they're not the same. And this plot is difficult. It maybe look strange to understand at the beginning, but this is looking at surface air temperature anomaly in about 7,000 regions. So you compare all of them with all of them. Okay? So you have, like, I don't know how many mutual information values, and you have, I don't know how many cross-correlation values. And then you plot them in a plane and plot in color code the density of points. So when you have this region here, means there's no correlation, basically, and there's no mutual information. Then we have another region in which there is correlation and there is mutual information, up here. Okay? So here you can detect interrelationships with the cross-correlation and with the mutual information. And then there is a region over here. This one is the one that the mutual information gives you more interesting results, because in this region, the cross-correlation is below some threshold, which you consider significant for the data, but the mutual information is above the threshold that is significant for that data. So let me start again. For the type of data, you consider that a cross-correlation above 0.7 is significant, and a mutual information above 0.4 is significant. Okay? And in these points here are those points which you uncover something with the mutual information in which you don't see with the cross-correlation. Okay, another thing is to say, okay, this tells me whether the data is independent or not. How about if this is synchronized? How about if the two time series are synchronized? Well, a way to find synchronized events, because maybe the time series are not synchronized, but some events in one time series are somehow correlated with events in some other time series. This is an example of EEG signals from some rat. And you can see the left and right electrodes, which are separated, and you can see that there is some oscillations which are correlated. So how to detect if these events are synchronized or not. You use a threshold in both time series, and then define the events, and then count how many events in each time series occur, and how many appear in X shortly after an event appears in Y. And you do this analogous for the other situation. So an event appears in Y shortly after something happened in X. And then calculate these magnitudes, which give the different type of information. Here, mx is the number of events in each time series, and these are the numbers you counted on events related that occur in one with respect to the other, and this is this parameter tau. Again, you need to select appropriately this window. But then if Q is equal to 1, we can say that every event in one time series is followed by an event in the other time series after a given time. And if this small q is 1, then we can decide the direction of coupling, because the events on X always come before Y. So there's you can speculate that there is some sort of causality, because X always occurs before Y. So let me say that this has been used many times, this event synchronization. I wanted to point out this example in which they study disasters, climate-related disasters, and how these climate-related disasters come before some conflicts. So there's some conflicts and there's natural disasters, and you can see that maybe this one comes after this one, and this red comes after this green, and so on. So you, of course, have to use a threshold to define what is a climate disaster, what is not, and also see if you can find the reasons for conflict. So I think it's an interesting application. If you're interested in this, there are many more examples in climate, for instance, how precipitation in one region triggers events in another region later on. So this is this paper where it was proposed. Actually, it applies to brain signals, but it has been some method that has been applied in many situations to detect synchronization in time series. And maybe it can be applied in social terms, because it's some topic in one region. People start talking about this. Then if you look to another region, you will see that people start talking about that too. So that's the idea. Okay, so but now causality. Causality, the typical way, or the classical way, is to look at Granger causality. How many of you are familiar with this idea? 2, okay. Well, okay, so first of all, this has a strong hypothesis. Two time series are described by stationary, autoregressive, and linear processes. This means that the future value, or the value at time t of a time series, depends on the past. And it has, we can represent it by this equation, some terms here, plus a residual, which is not explained by this equation. This is the past of X. And this is some residual. And then another time series, the same time series, can be considered that depends on X, but also on the past of another, of X2. If you model your data using this equation, which is linear, you get a different error with respect to ignoring the past of X2. So if you manage to decrease the error, the residual, we can say that this information improves the prediction of X. Knowing the past of X2 improves the prediction of X1. And that's the idea of Granger causality. X2 is causally related to X1 if the residual is smaller. Yes, yes. Okay. We're talking about Vivariate, so we have a time series X1 and a time series X2. Okay. this is a linear method, and the one that is, this guy got the Nobel Prize for this paper. This paper it's one of the most cited papers, has been used in economics a lot to detect causal relationships, but it has this constraint. It has to be, the data has to be stationary, and it should be described by these linear autoregressive models in which
what is the meaning of stationarity?
stationarity is the opposite of the temperature that I showed you on one slide, that you saw that the temperature was growing.
Yeah.
Stationarity is a process that's supposed to be stationary. It doesn't, there's no drift parameter that is increasing the temperature or no, there is fluctuations, but there is no, you can, of course, remove the trend. You have, if a time series has some trend, something like the dollar tends to go up, right? You can remove the trend, and then, okay. The transfer entropy is a method that is related to grand shared causality, but has a different idea, and is the conditional mutual information, assuming that we know the past of one of the two variables. So basically, I'm not giving you formulas, but I give you references where you can find them. This is the mutual information of X and Y, considering that you know the past of X. I'll give you examples in a minute at least. And you can do the same for the transfer entropy from Y to X. Is the mutual information between Y and X, considering the past of Y. The mutual information, if you remember the expression, was a symmetric quantity, but these are not necessarily symmetric, and that gives you the possibility of defining an index. Just by the difference of these two, you can detect some causality in one direction or in another. If you have two Gaussian processes, X and Y, then it has been demonstrated that transfer causality and grand shared causality give you exactly the same results. And the advantage of transfer entropy is that, again, is computed from probabilities, these conditional probabilities, and can be calculated using symbols too. That is known as symbolic transfer entropy. Again, this is a very good report on causality detection, and this is the original paper proposing the transfer entropy, which is actually measures the transfer of information. It actually tells you if this time series is informative to improve the prediction of another time series. That is basically the idea.
It's hard to calculate the transfer entropy, or?
I'll give you an example in a minute. So basically, there are problems because you can use these techniques to identify where is the information. If I want to predict, and this is an interesting story because there was a while ago, there was a competition with $1 million reward who could predict the power consumption of France, okay? They wanted to predict the total power consumption of France. So if you want to predict this, where is the information? Which variables you should take into account? Is it important to know the temperature? Obviously, yes. It's important to know the winds that are producing energy, and so on. So of course, there was a lot of people participating in this, preparing whole year, working on this. And of course, you can use machine learning. No? You give a lot of data, all the data they have, all the time series that you think are relevant, and then you try to predict what is the next step in one of the time series, which is the energy consumption. But the guy that won this is a scientist working in the Basque Country, and he did it not using machine learning. He didn't use machine learning. He used one of these expressions that I'm giving there, an autoregressive process. Okay, so the variable depends on the past of a lot of others, and he was able to select the time series that are informative, which is not the same as causality. They are informative. They allow to better The difference was like 1%, but 1% improvement in the prediction was good enough, because we're talking a lot of money. The guy got the million. He had to pay half for taxes. But anyway, it's very interesting because the way he solved the problem was using this type of analysis, no? Writing an expression on how the variable depends on many other variables. And which ones are relevant, which ones are, and weight, of course, you have to weight them in different ways. So yes, these methods might not give you if there is a link between X and Y and zeta. It might be you might detect causality and it might be indirect. It's not a direct link. Or it might be a causality between X and zeta, but it might be because there's a common driver. For instance, the sun. The sun drives the temperature all over the world. So that doesn't mean that there is a causal relationship between the temperature in Uruguay and in Sao Paulo. Maybe, but these methods give you maybe if you use to build a network, you need to keep in mind that those links, they don't necessarily reflect direct connections or real connections. But at least they give you information on where to get the information. I think these are without battery. No, this is it. This is it. OK. So yes, it's computationally demanding because you need to compute probabilities. And it's a probability in a three-dimensional space, not like the mutual information that is X and Y, but it's X, Y conditioned to another variable. So that means that it's conditional, it's computationally demanding. And a simple expression is to say, OK, we know that the mutual information for Gaussian processes has this expression, and we can translate this to the transfer entropy because is using conditional probabilities, but it's possible to go from this expression to expression for the transfer entropy that is still valid only if the process is Gaussian. But we can use it anyway. We can use it even if the process is not Gaussian. So this is a simplification of the expression. But if we use this simplification, here we do not have to compute any probability. We need to calculate cross correlations. Cross correlations are easy, much faster to calculate than the probabilities. So yes, you can test this method, and the software is freely available here. You can try, well, I'll give you the link in a minute. But yes, we try this. We know we are using an expression which is not valid in reality, but it gives you a possibility of computing fast results. So, what the,
sorry.
Yeah.
You can use a lag cross correlation. It has to be without lag.
No, here you can put the lag too.
You can put
Yes,
the
yes, yes. Yeah, yeah. So basically what we did to test if this was possible, if using this approximation is good idea, we consider some data generating processes, like 14 or something, in which we know if there's coupling or there is no coupling. For example, the two first model, they are independent. X and Y are independent. We don't expect any causality. And we have several models in which there is causality from X to Y, from Y to X. I'll just give you examples. And then there is an example in which there are proposed directions. And there is some models which are over here. Some are linear and some are non-linear. So notice that these cases are all, oh no, this is non-linear. So we did consider different models with linear or non-linear, and this is with delays, and I think we also added some longer delays. So which models we have are you can find them in the reference before. To do, of course, you need to test whether you find causality or not. So you cannot just keep a number. You need to do many simulations and contrast with a situation in which there is no causal interactions to detect, to filter out things that are not significant. And then you can say, well, if I say, yes, there is causality, is this correct or not? So that is called power. there is causality and we find causality. It's what is called, in a different context, it's called true positive. I detect causality and there is causality. And the size is, I know the model, I know there is no causality, but I find it. Because I do my significance analysis and I decide that my value is significant. So this is a mistake. It's called false positives. And here are the results. So in 100, this is a percentage. We did 100 simulations. And we found causality very, very, very small percentages. So this is kind of good. We made 2% mistake, 3% mistake. When there is causality, sometimes we find them all the time, 100%. There are some mistakes. We find X to Y, but there is no. And here, there is causality in the two directions, and we find it. But there are, you can see here, there are a lot of mistakes. These two models, here we don't detect the causality 100%. Here we have, these are chaotic systems. The two models display chaos, and therefore those are not, our results are not good. They don't work in that case. Okay? And if we compare with other methods, we compare with Grand-Shell causality and transfer entropy, basically we get very similar results with Grand-Shell causality. And transfer entropy also doesn't work when our methods do not work. So basically what I'm trying to tell you here is that the method is not perfect, but other methods do not work either. Okay?
How you compare the trended and in non-stationary series where the Grand-Shell causality cannot be used?
I use, no, because if there is a trend, you can remove the trend.
Okay.
The trend and then use.
Okay, and it will always work.
We can always apply removing the trend.
Yeah.
And if it's unseasonality, you can remove the seasonality too. Yeah. We did apply to El Niño. And there's well known that there is an interaction between El Niño and India, the rain in India. But of course, what the message of this slide is depends on the resolution of the data and how much data you have. If you have yearly sample, we had 150 years. If we had monthly sample, we have much more data. And these are the results for the pseudo-transfer entropy. Detects the main causality, which is El Niño is the dominant climate effect, so this is trivial. Grand-Shell causality also detects the same. And El Niño and transfer entropy detects a weak link, a weak influence from the India to El Niño. But in monthly data, the results change. So this is the type of things you need to start getting used when you deal with this data. On a monthly time scale, maybe India influences El Niño, while in a year-long time scale, then this phenomenon of El Niño that repeats every 3 or 5 or 6 years affects India. Okay, so depends, and again, Grand-Shell causality gives the same, while transfer entropy detects both. So how much can we save? How much time can we save? It's interesting to see that, suppose that you have 500 data points, wherever they come from. In this case, it's 1 data point per month, 40 years, and you want to compute the transfer entropy, is 112 milliseconds, and the approximation expression is only 4. If you want to use this to analyze El Niño region, in this region, there are many points, 8,000 data points. That means you have to compare 1 million pairs, okay? So this takes a lot of time. If you want to do it properly, without any approximation, it will take you 800 days. If you use the pseudo expression, it will give you a month. It's still a lot of time, but it's doable. And this is without doing any surrogates. But if you want to test the value, if it's significant or not, you need to, for each pair, you need to generate your surrogates, calculate your histogram, and see if your value is inside the histogram or not. Yes, you save a lot of time, but there's no free lunch. What does it mean? It means that we know for sure that it doesn't work if the system is highly nonlinear or chaotic. if you want to try it, is here, and it's very well explained as far as I know, so you're more than welcome to try to infer causality between two time series, I don't know, the predators or things like that. Okay, so besides Granger causality and transfer entropy, there have been many, many methods. So if you start looking at the literature, of course you have the symbolic approach, partial correlation, in which you look how two variables are partially correlated, partial directed coherence, cross-mapping, partial cross-map. If you want to look at the reference, this is a few years old, but it's an interesting comparison of 6 methods. And you will see that the results might depend on the methodology, and you might find causality or not, depending which method you use. Here I put an example from social sciences, which is the social media. And they use symbolic transfer entropy to analyze microblogging time series. And, well, if you are interested on this, it's quite a good point to start looking at how it has been applied in the context of socio-economic systems and references in there. Okay, so if there are no more questions about this, we go to, you don't have only 2 time series, now you have a lot. So let's say that the first thing you can do with all this all time series is to build a network. And in that case, you compare pairs using cross-correlation, mutual information. That will give you undirected links because that's symmetric. You can use causality, causal measures, and that will give you directed links, and you obtain a directed network. And let me put a classical example that comes from brain function, and this is work by Dante Chialbo, the original work. So you have all your time series from brain activity, calculate the matrix of cross-correlations. Here is in color code, the cross-correlation value. You use a threshold and transform this in black and white, 0 and 1. And then you can graph, plot your network using some visualization that you like. So basically, to obtain an adjacency matrix, you need to use a threshold. And the similarity index that you use, let's say the mutual information, if above a threshold, the 2 pairs are connected, otherwise they're not connected. People have done this functional approach in many contexts. I just put this example of a network that is constructed from synchronized events. So they calculate the magnitudes that I showed you before, the Q, the big Q, the small q, and then they use a threshold, of course, to decide, yes, here the events are really significant correlated, and this Q value is too small, not significant. And they found a teleconnection pattern from, for instance, here affecting almost all over the world. This is a paper published in Nature a few years ago that analyzes extreme rainfall. So once you have your network, how do you do to characterize? This is what Vicky was talking about, so I'm not going to repeat what she said. But the only thing I want to point out is that typically people first look at the degree distribution, as you know. So the degree can be a delta if the network is regular. It can be some distribution if it's random, or it can be a power law if it's scale-free. How do you characterize a distribution? In the same way that you characterize any distribution, mean value, variance, skewness, kurtosis, and so on. And how do you compare two distributions? So how do you compare two networks? Whatever distribution you extract from your network, let's say the distribution of path lengths, the distribution of assortativity coefficients, degrees, whatever, there are many ways to compare two distributions. And that's the typical EC is a Euclidean distance. But this means that the two distributions should have the same base, should have been the same number of bins. Otherwise, it's not possible to do this if one distribution has 10 bins and the other 100, right? So there are other ways based on information theory, which is Kullback distance, okay? which is the entropy of one distribution and the entropy of another distribution. Okay? So from each distribution, you compute the entropy, and then you subtract. In this case, you can compare distributions that can be very different. Don't need to have the same number of bins. Okay? And not necessarily the entropy. You can use an information measure. I talk about entropy, but there are other measures, like Fisher information or... So with the distribution, you compute an information measure and then compare. Or you can calculate the Hensen divergence, which is the symmetric distance, because this might not be symmetric. So that's not appropriate distance between distributions. Okay? So you can make this symmetric, and this is very popular, a very popular way of estimating how different two distributions are. And in this paper, you have, I don't know how many distances. There are many ways to define distances between distributions, and again, the results you get are more likely to depend on how you measure the distance. Of course, the clustering coefficient and assortativity are ways to characterize a network, and how many connected communities or components you have. So basically, when you do time series analysis and you get your functional network, in the way I say, you compute the cross correlation, do a significance analysis, retain only the significant values, you need to use a threshold to decide this is significant, this is not significant. And the problem with thresholding is that as you increase or decrease your threshold, you change the number of connected components. So if you choose a threshold that is very low, the threshold increases like that. So if you start with a very low threshold, your network is just one big component, right? Everybody's connected to everybody. And you have the number of components is basically 1. If you start removing links, because you increase the threshold, you start getting increase the number of components. If you put a threshold that is very high, you end up with disconnected nodes, each of them being a component, so you have a large number of components. Now, how this depends on the threshold, if you have different networks, we'll have a different variation, okay? If you choose, let's say, network A from, let's say, brain signals of a healthy patient is like this, and if the person has Alzheimer's, let's say it's like this. If you use this threshold here, or use this threshold here, you will see that the network is very significant. I think I don't have this video. Yes, see, so as you start removing links,
you are removing the link based upon weakness?
You remove the link because you increase your threshold, and then because your significant threshold is very high, the link is not significant anymore. So your cross correlation, you put 0.5 as a threshold. Everything above 0.5 is significant. But once you change this, the 0.52 is not significant anymore. So you remove these links. You start removing. Oh, no, I wanted to show you the video again. But as you remove, you get up a lot of components. So basically, persistent features are true features, features that persist when you change the threshold. If you use this threshold, the two of them, the two networks look similar in terms of the number of components. And if you use this one, they also look similar in terms of the number of components. But the networks can be very, very different. So that's why it's important to check what is the effect of the threshold that you use to build the network. And the last problem that I wanted to talk about is how to infer the network from data. Suppose you have the data and you want to find out how the system is connected. Which are the real links? Which are the links that do not exist? So we know that if the significance, if the similarity measure is above a threshold, they are connected, otherwise they're not connected. And how can you select an optimal threshold if such thing exists? But we also want to keep weak but significant links. If you use a very high threshold, you're removing a lot of things that can be significant. This is a problem, for example, when you have spatial networks, because when you have spatial networks, points that are nearby will be highly correlated. But you don't want to have these trivial connections. You want to see other connections with regions that are far away. So it's important to try to see how to keep these weak but insignificant links, and in the end, it's a classification problem. You have to find the optimal threshold such that detects the ones that exist, maximize this detection, and minimizes the mistakes. For that, you have to use something that is called confusion matrix. Who's aware of this? Who's familiar with the confusion matrix? Okay. So basically, for each threshold, you get 4 numbers. The ones that you think they're not significant, and they are not significant, so this is the true negative. Then you predict that some link is not significant, but is actually significant, so yes, it's a false negative. The true positives and the true negatives, okay? The true positives are the ones that you detect and exist, and the false positives you detect, but they don't exist. So from this, you can define many measures. Here you have the most popular one, the accuracy, how often the classifier is correct, the misclassification, how often it's wrong, and so on. The ones that are very well used are the true positives and the false positives. These two, true positives and false positives. The true positives are called also recall or sensibility. When it's yes, how often do you predict the yes? And when it's no, how often do you predict yes? And then there is also the precision. When you predict yes, how often is correct? Let me show you some examples of how to use this. So you have 2 classes, the links that exist, the links that do not exist. The links that exist, you expect that the significance values will be higher. If you are using the right measure, you should capture significance values higher, okay? And the values, the distribution for when they don't exist, they should be lower. See, if the link exists, the correlation should be high, and if it doesn't exist, the correlation should be low. But of course, there is not a clear boundary, so if you use a threshold here, you will be considered all this part of the distribution as positives, and these are false positives because they don't exist, okay? And if you put this threshold here, all these, which are true positives, are positives, they will be false negatives because you put in them, you don't detect them because they're below your threshold, okay? And that gives you the way to build the receiver operating characteristic ROC curve, and I will talk about the precision recall in a minute. So basically, depending on which measure you use, you get different ROC curve, okay? When you change the threshold, let's say that you start with a very low threshold. With a very, very low threshold, you detect everything. Everything is positive. So no, because everything is significant if your threshold is very low. So that means you detect everything positive, but you have a lot of false negative too. So you start up of this line. As you start increasing your threshold, you hopefully remove only the mistakes. But typically, you also remove the things that you want to detect. Ideally, you will move along this horizontal line, detecting everything you need to detect, and reducing the false positives. Ideally, you will move up here and then down here. At the end, if your threshold is very high, you don't detect anything, no? You end up with everything being not significant. So the area under the ROC curve gives you, lets you know how good your procedure is and how to select the threshold. The best threshold, the best method, the best measure would be the one that gives me the highest, the largest area. Ideally, it'd be a 1, okay? And which threshold is the one that takes me something like this? Something like this will give me a good compromise in between detecting what I want to detect and making no mistakes. If you do it randomly, just throwing a dice, what do you expect? You would go through the diagonal. A random classifier will randomly detect true positives and true negatives in the same way. So anything that is better than this diagonal will be useful in principle, will help you detect what you want to detect, trying to avoid mistakes. When you have to classify and one of the classes are, when the classes are unbalanced, for instance, if you have a network and it's sparse, most of the links do not exist, then it's more informative if you do a plot that is similar to this one, but it's called precision recall. And this is because, again, I don't want to go into details, but this is because these two numbers do not depend on the number of negatives, whether there are 1,000 links that do not exist or 10,000 links that do not exist. It allows you to detect few elements. Okay, so yeah, I'm getting to the end. This is just an example where we test this, and you have it in the slides, so you can look at it. We test this method using a data generation process. So we know, we use a Kuramoto model, we know how the oscillators are connected, we know this matrix is random, and then we pretend we don't know it and try to see if we can fully recover the network, okay? So basically, if we analyze the phases and we use cross-correlation, mutual information computed from ordinal patterns, what does it work better? Okay, of course, to detect the oscillators, they need to be coupled. So if they are not, the coupling is not good, we don't see, but we can get the true positives almost to 1 with the cross-correlation. And the false positives do not go to 0, but it's still the cross-correlation is still the best way to try to find the network from data. Now, the phases are usually not, it's not a physical magnitude. It's not an observable. Usually you observe a function of the phase. So you don't measure the phase, you measure the cosine or some function, some periodic function. So let's see what happens if we look at the observable, the sine of the angle. Then it's horrendous. There's no hope. You cannot recover the network from observations if you don't observe the phase, if you just observe a function of the phase. And these are the tiles, and here you have the reference. And if you look at the frequencies, because remember, if you know the system is coupled by the frequencies. These are, if we put the derivative on this side, this is the frequencies of the oscillators. If you look at the frequencies, then the cross-correlation, again, is the one that works the best because it allows you to get the true positives equal to 1 and false positive 0. However, this is a small network. The coupling is symmetric, so we don't have too many things to find. And we had plenty of data points to analyze. The time series was very long. In Array, there's lots of people working on network inference, network reconstruction, network prediction. There are many methods that have been proposed to do this. And the literature is very, very extensive. And I'm going to finish here talking about a basic limitation of network analysis, which is typically interactions are not between two nodes. typically, some cases, there might be high-order interactions where there are 3 or more nodes that participate of the activity. That is described by Simplician Complexes. Who is familiar with Simplicial Complexes? Okay, brilliant, brilliant. So basically, this is an example of what this means. You have neurons, 4 neurons that fire, and sometimes the cyan and the red fire together, sometimes the cyan and the blue, and sometimes the 3 of them, okay? So if you represent this on a network, you will see that there is a connection between these two, and these 3. So you
next, you have the slot of times. Which is the dimension of this?
This is just an example.
No, in the matrix side.
These
column
3.
You have the number of neurons.
This is the number 1, number 2, number 3, and horizontal is time.
It's time. Okay.
So this says that these 3 act together. Yes.
How can we distinguish a three-body interactions from 2 simultaneous two-body interactions?
Yes, very good question. Next question. No, I don't know. I really don't know what to tell you. I'm not sure if there are methods that can allow you to distinguish high-order interactions from bivariate simultaneous interactions. I don't know. I can give you some reference here on how to deal with these simplicial complexes. But basically, a node is a 0, a link is 1 simplex. When you have 3 nodes acting, it's a 2 simplex, and so on. And you have this. So it's very complicated mathematically. The mathematics under is very, very tough. And I'm not sure if there's any practical way that has been demonstrated to work. I don't know. Anyway, so multivariate analysis uncovers interrelationship when you have data sets with many time series. Different similarity measures or causality measures are available to use, so you can infer. They will likely give you different results. You recover different properties. If you have to use thresholding, if there are unobserved variables, some hidden nodes, all of them make very difficult to recover the structure of the network. And well, yes, this is very fast evolving, and maybe you need to be really up to the literature because papers are coming all the time. And new methods, especially in the simplicial complexes, is a very highly active research area. So I want to finish my part by acknowledgement. This work I presented was done by former PhD students. Julio is the one that did the network reconstruction that I show you, with the cross correlation being the best measure. Aragoneses, he worked on the transition. When you put a threshold and you calculate the entropy different ways, you see a sharp transition that you don't see otherwise. Carlos Quintero did work on the EEG analysis, trying to separate eyes closed and eyes open. And Ricardo developed the pseudo transfer entropy that can save you a lot of time. And the announcement is, if you want to check the webpage, we have this Mediphenol conference coming up in December. That's all. Thank you for your attention. Sorry, I forgot.